Very sexy fact.
Right.
Yes, thank you. So I'm a clandestine from the other program. So the title was Crawling Motility, but this was due to an exchange of email. That was the topic, but I would like to talk about other forms of motility also, like swimming. So it was going to be both. Okay, so very mixed audience as usual. Let me give you some, let me start slowly and then I will maybe go faster towards the end. First, the topic. Motility is the ability to go from A to B with a purpose. So this is a motile object. It's an example of a motile object, something that can go straight, right? And I will, it's a toy. I will use this as the, somehow the metaphor and the paradigm for the whole talk. I will talk about things that are much more complicated than this one, but I would like to think about them with the same frame of mind with which you think to this object here. So a major difference between the biological motile things I will talk about and this one is size. So this one is 2 centimeters. The object I want to talk about are at the micron scale. So maybe 2, maybe 10, maybe 50 microns. Okay? And cellular motility is one of the main examples for motility at 1 micron scale. And here are some examples. This is crawling. So this is a form of motility that, like this one, uses the interaction of an organism with the surrounding world based on friction, adhesion, tangential interaction with a substrate. Okay? But these other two, this has been shown by Carsten Kruse some time ago, a couple of weeks ago, a similar thing from the same lab. So this is a sperm cell that swims by sending bending waves in the flagellum. And this is another famous example. It's a bacterium, much smaller in size, where the tail, where the flagellum has a different structure, and these are rotation of the flagellum, which acts like a corkscrew. Okay? So these are the type of things one wants to talk about. And one thing that they share with this is the fact that there's a motor. So this thing is propelled like, I mean, another metaphor is a car. You know, there's an engine, there's something inside that propels it. Okay? And this is true for each of those things. And it's something that we should keep in mind. However, an integrative view, which is the one I advocate by looking at this. So you want to see the organism in its everything, you know, from the engine to the... So an integrative view of these systems is coming along. It's not there yet. And so I will talk about patches of reality in some sense, whatever I manage to understand, etc. So let me start with theory. Okay, so let's do some basic theory. And okay, the starting point. Let's do it with swimming because it sets the stage. And okay, swimming in a fluid. The fluid is governed by Navier-Stokes equation, maybe, but if you go down in scale, down in size, the right inertia forces scale in a different way with respect to viscous forces. The Reynolds number tells you that, and you are you are led to neglect inertia completely and to use Stokes as the right equations, and you change the framework of your equation. The equation of motion are no longer F equals ma, but F equals 0. Okay, so let's see let's look at the consequences of that. Maybe I should say, I mean, there are many people in geometric mechanics in the program, but I don't see them in the audience. So, okay, I will say these things nevertheless. I mean, very easy for them, not very easy for me. Reynolds number. So if you do swimming in a certain medium, like water at room temperature, rho and eta, the density and the viscosity of water, are essentially a constant. 10 to the 6 meter over second inverse. And so the Reynolds number is set by the typical length scale and typical velocity scale of the flow. The length scale, okay, the size with the fluid at rest at infinity. The velocity, the swimming velocity. Again, the fluid that's at rest at infinity. And because of metabolic reason, the swimming velocity tends to be related to size as well. So size in this thing comes with the power 2, and it becomes very important. So if you are a 1 meter person swimming at 1 meter per second, so at 1 body length per second, so gauge it against Michael Phelps, 2 meters, 100 meters in 50 seconds, it means 2 meters per second, 1 body length per second. Okay, so if you have 1 and 1 as V and L, the Reynolds number is 10 to the 6. If you are a 1 micron bacterium, so 10 to the minus 6 meter, swimming maybe at 1 body length per second, so 1 micron per second, you have 10 to the minus 6, 10 to the minus 6, 10 to the 6, 10 to the minus 6 is what is left to you. And so the Reynolds number goes from Michael Phelps to the bacterium from 10 to the 6 to 10 to the minus 6. Okay? Conclusion, Michael Phelps swims by accelerating water. Rho, the inertia, is the driving thing. A 1 micron sized bacteria moves by exploiting resistance to motion. And you hear the paradox in this. You move by exploiting resistance to motion. It's like a corkscrew. So you have to do something clever to turn a resistance into a propulsive force. Okay? So this is somehow, in a nutshell, a topic that has attracted a lot of attention. Let me skip the hand-waving proof with the hands of G.I. Taylor very quickly. G.I. Taylor showing the scallop theorem. So this is a scallop in a sense. So it's more a rudder, but it's a way of propulsion that works by doing this. It works at high Reynolds number, so in water. But if you decrease the Reynolds number by ramping up the viscosity, you go nowhere in average. Okay? So there is some motion, but no net motion in average. Okay? And the reason is the fact that the type of shape changes that you're exploiting are too poor. Okay? And as you will see, this leads to no net motion. So in a sense, both biological motility and can be seen in a sense as a struggle against the scallop theorem, in the sense that nature has found ways around it, and so nature has successfully beaten the scallop theorem. And so these are the flagella I was showing you before. So if you are not moving a rigid rudder, but you have the possibility of changing the shape of the rudder, and you maximize the resistance of water in the power part of the stroke, and you minimize it in the recovery part of the stroke, you break the time reversibility of the shape change, and you beat the scallop theorem. And the bacterial flagellum is another story, but I don't want to play it too much. Now, this is nature. Now, imagine you want to reproduce motility at the micron scale. You have the same problem, but now at the engineering level. So you have a constraint on the complexity of the mechanisms that you can exploit, because you have to manufacture it at 1 micron, so you cannot do very crazy things. And on the other hand, it should be complex enough to beat the scallop theorem. And so this is an example of a system that works, in quotes. It's a model system, which has, again, attracted a lot of attention. It's made of 3 spheres, rigid, and that can, through a system that is not part of the hydrodynamics, that can change the relative distance. And so it's not immediate to see it from the movie, but what the movie says is that if you do it in a clever way, which means not like this, but with a cycle like this, then you manage to move. So you can get a periodic shape change. So after 1 period, you go back to the same shape, and produce a non-periodic positional change so that you do not go to the same place. Okay? So this is what you want to achieve. Okay, so if we want to do some theory about this, what do we have? I mean, the obvious ingredients. We have the equations of motion of the fluid and the equations of motion of the swimmer. We want to combine them, and we want to obtain the fact that we read the problem as, for example, I prescribe shape changes, and I solve for positional changes, and I get net motion. Okay? So let me show you a way of doing this. And let me make a little preview of what's going to happen. So the equation of motion of the fluid means that what we're really interested is to solve the equations of motion outside ourselves, using as datum our velocity, the velocity of the part of the swimmer, of the solid, which is in contact with the fluid. And through the non-slip boundary condition, whatever I do with my hand is transmitted to the fluid. Okay? The fluid doesn't like that, and it reacts, action and reaction, with a force, which I call F. And that's the force, the propulsive force I'm going to use. Right? So swimming means you disturb the fluid and you receive a reaction that propels you. Now, at 1 micron, the fluid is governed by Stokes. And so you expect, okay, if you were a sphere being dragged rigidly, you know the force on that sphere. It's the Stokes formula. So the force is 6 pi, the size, the radius of the sphere, the viscosity of the fluid, times the velocity. Okay, so you get a linear relationship between force and velocity. Okay, in general, one expects something that depends on, we have a more complicated object than a sphere. We may describe its state by position and shape. Okay, so any object can be thought of as positional variables and shape variables. And so we expect that this force will be a function of state and of rate of change of shape, of state, like for the velocity. V is the rate of positional change, right? So we expect something that is a formula that depends on c, position, say, and c, velocity, and their time derivatives. Okay, so that's what one thing that's going to happen. The second thing is that the way this moves is governed by the equation of motion of this thing. So F equals ma, for example. Now we are neglecting inertia of the fluid. We neglect inertia of the swimmer as well. And then we want to do self-propulsion. So there's nobody pushing. And maybe we neglect gravity and other external forces. We do neutrally buoyant swimmers or stuff like that. And so this equation becomes this, because there's no gravity, there's no other external forces pushing, and there's no inertia. So it becomes F equals 0. Viscous forces equals 0. So the one on top equals 0. Okay? And so this is a constraint. So this is something that constrains position to shape, which is exactly our intuitive notion. We change shape and we cause position, right? So position emerges from a constraint on shape, right? And so if you now think of constraints, blah, 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 if you want to be able to change position when shape goes back to the same place, it means that this constraint must be non-holonomic. Because if it were holonomic, there would be only one position for every shape, okay? So this is what swimming is about. So I propose to see this scheme for the model case of the three-sphere swimmer and to learn something, maybe to learn some secrets, and then to try and export these secrets to the context of crawling motility. Okay? So this is the three-sphere swimmer. And it's described by 3 parameters. So I'm assuming that the center of the spheres only move along a line, right? So once you know the position of the center of the spheres on the line, you know the position of every point of the system, right? So x1, x2, and x3. However, you can also parameterize this with the position of the center point of the center of the central sphere, for example, and the distances, psi1, psi2, because c plus psi2 gives you x3, and c minus psi1 gives you x1. Elementary, and we can take the time derivative, and so we link the velocity of the center of the spheres and of any point of the spheres, because they are rigid, to the rate of change of position and to the rate of change of shape. So I'm calling psi1 and psi2, or the vector whose components are psi1 and psi2, shape. And it's, let's test that this is a good definition. So a good definition for shape should be that, for example, if you freeze shape, then you are rigid. Okay? So if you move at frozen shape, you move rigidly. Now, if you move at frozen shape, you move at frozen distances between the 2 spheres and the central one, and so you move rigidly. Okay? So it works. So for cells, this step would be a bit more complicated, but conceptually similar. Okay, now we have to write down the equation of motion of the fluid, the equation of motion of the swimmer, combine them, blah, blah. Let's do it. So the essential equation is that the drag, the total force, the total viscous force, its component along the axis should vanish. Okay? So F equals 0. Now the way F looks in this problem, so the notation is here to remind me and you that what we are doing, in some sense, it's replacing the fluid with a map, a mathematical map, that transforms the Dirichlet datum, the velocity we apply. We solve the outer Stokes problem. We compute the stresses in the fluid. We integrate the stresses on the boundary of the sphere. We get the total force. So we transform the Dirichlet datum in the Neumann type datum, the stresses, and we integrate. Okay? So that's the step, in some sense, that replaces the fluid. The fluid is represented by this map. Okay? And the reason the notation is like that is that this map depends on shape, because if you do it on different shapes, you will get different solutions. And it depends on the datum, the Dirichlet datum. And the square brackets in my notation means, however, linearly. Because of Stokes, the stresses depend linearly on the velocities, right? So this means that we are trying to compute a number, just one number, the component of the viscous force along the axis, for any shape, for any velocity distribution, but this number is a linear function of the velocities of the Dirichlet data that are linearly related, so it's these relations here, to the rate of change of shape and to rate of change of position. So this is a form, a number, which is a linear form in C dot, psi1 dot, psi2 dot. And so you can write it. Anybody can write a linear form in these three quantities. It's a matter of writing down the coefficients. So some coefficient phi1, which depends on the state of the system, some coefficient phi2, which is the coefficient of psi2 dot, and some coefficient phi3. So what is the meaning of these coefficients? Let's look at the simplest of them. So I've lost something. So these coefficients, I wrote, they should depend on the state of the system, true, but not on the position because of translational invariance. Let me comment on this in a second. Let's look at one of them. Yes?
Do you have a motor in each sphere?
No, the motor, in some sense, it's in the link between the sphere, but I'm not resolving it. The motor says that I can change the distance between two successive spheres, but I'm not, it's a God-type motor. I'm not resolving it. I'm not computing the power. It can do anything that is needed, so the data is the shape. Maybe I should emphasize this. In all of this, I'm considering shape as freely prescribable and known. Okay? So this is a strong assumption, which is not, it will require an extra step when I will ask myself, how do I prescribe these shapes? But in this description, I'm assuming that it's known and controllable. Okay? Which one is the, okay, I'll try one. Okay, so let's look at this phi3 to have a feeling of what's the meaning of these quantities. So what is phi3? So phi3 is, let's look at the left-hand side. It's conceptually, it's a viscous drag. It's a force, right? It's a force, it's a component along the axis, the x-axis of the viscous force that the system experiences when, now let's look at the right-hand side. Let's set psi1 dot and psi2 dot to 0, and let's put c dot equals 1. We get phi3. So phi3 is what? It's the drag the system experiences when it moves at unit speed rigidly. Okay? So if the system moves rigidly at unit speed, then the drag is phi3. Okay, so it's obvious that it's independent of c by translational invariance. So if I move the system at unit speed here or here at same shape, I get the same number. And this number is non-zero if the radii of the sphere are non-zero. And we know this so well that we even know the sign of this number because it's a drag. The name comes from this. It's opposite to the velocity because it's drag. It resists. If I move in this way, the force will direct it in that way. And so it would be non-zero, right? Very well. Since it's non-zero, this is a nice equation in C dot that we can solve for C dot. We divide by phi3, which is non-zero, and we obtain C dot. So here is C dot. And this is the equation that solves the problem I was mentioning before. I assign the rate at which I change shape. I get the rate at which I change position. Okay? And here is the equation. So these V1, V2 are things that are ratios of hydrodynamic forces, of viscous forces. We have discussed explicitly the phi3, which is in the denominator, and the other two are sort of obvious. Okay? So we have talked about phi3 in particular, and this is the equation. Okay? Let's pause a second. Very innocent looking. Maybe I should also emphasize the fact that if we did a general problem in which the state of the swimmer is not, I mean, it's a more complicated swimmer in which its state is position and orientation. We have to describe also the orientation. Nevertheless, exactly the same framework will apply. And instead of having a non-zero coefficient, we will have a resistance matrix, a symmetric and negative definite resistance matrix. And we could do exactly the same thing, except instead of having one ODE for the motion, we would have 6 ODEs for the rate of change of position, so the translational velocity, and for the angular velocity. Okay? Very well. But now let's go back to the equation. Let's look at it a little bit. So it looks very innocent looking. It's an ODE. So let's think about possible consequences. Let's remember that what we are trying to do is to change position by assigning a periodic change of shape. Okay? So we have functions, xi1 and xi2, periodic of period t, which means that psi of t, as a vector, xi1, xi2, is equal to psi of 0, okay, if t is the period. Right? So we change shape. After one period, we go back to the same position. Now, let's imagine that these things are constant. Okay? So what I'm asking myself is whether the coefficients of this ODE are shape dependent or not. Okay? So imagine that they are shape independent. Well, then we have a linear relationship between the rate of change of this and the rate of change of that. And we integrate after one period. The right-hand side integrates to 0 because it's psi of t minus psi of 0. And the left-hand side becomes periodic. Psi of t equals psi of 0. And there's no net motion. Okay? So this is, the scallop theorem is like this. So this equation is simple ODE, and it shows to you that if you want to break the rigid link between causes, shape changes, and effects, positional changes, you need a nonlinear ODE. If it's linear, because the linearity in velocities is given on you, because you are Stokes. And so if you add coefficients that are independent of shape, then you go nowhere. Right? If there is enough nonlinearity, then this is no longer a linear ODE, because these coefficients are shape dependent, and you may get a non-periodic positional change driven by a periodic shape change. Okay? So this is contained in this observation. So this is nonlinear. You need nonlinearity if you want to get net motion. And you can get nonlinearity only if there is non-trivial dependence of those coefficients on psi. Now, instead of, I cannot do let's probe this non-linearity by looking just at the denominator, this phi3. So is drag shape dependent or not? Yes, because this is hydrodynamics. So the drag that I feel as a system, head and hands, when I move at speed 1, depends on the distance of the sphere from my head. If we didn't have this, we would go nowhere. Since this is true, then we have some chances to move. And why this is true? Okay, because, okay, let's use, I mean, one can prove this, but let's use maybe a simple argument. Because somehow, if we had the head and the hands very far away, say at infinity, maybe we can conceive the fact that we would get non-interacting, I mean, hydrodynamic interactions decay. So we would, I mean, the spheres would be very far away at infinite distance, and the drag on three spheres would be simply the sum. It would be 3 times the Stokes formula. It would be the sum of the drag on each individual sphere. But as we bring the hands closer and closer and closer, what happens is that there are hydrodynamic interactions in the sense that if I put my head in the wake of the flow, in the wake of this one, so I get the fact that this sphere is moving water here, I put my head here, and then I feel less drag. Okay? So hydrodynamic interactions make sure that this term is C dependent, is distance dependent, and so this becomes a nonlinear system. Okay? And so this is the way you can analyze the three-sphere swimmer. Probably you have done an analysis similar to this many years ago. I don't know whether you've eventually, I mean, I haven't seen it written, but I remember you talking about it. And so this is a way of reading what happens. And it's for this system, it's simple enough that you can do it with calculus in several variables, in the sense that what I want to do now is to compute the net positional change. So C of t minus C of 0. So I integrate C dot between 0 and t. I get C of t minus C of 0. And since C dot is given by the ODE that I was showing to you before, I have to integrate the right-hand side of the ODE. And I have V1, V2, which have this notation, so that we have set up a vector field. And the geometry that is emerging is the fact that C1 and C2 are 2 coordinates of a loop which is closed because C of t equals C of 0. So it's a loop in shape space that produces as a consequence a change of position. So we put position on the vertical axis, shape on the horizontal plane, that is the space of shapes, and we drive with loops in shape space changes in positional space. And what is the net positional change? It's the curl of, it's the integral, it's the flux of the curl of the vector field V through the area bounded by the loop. Okay, and it's a curl where the differential operator, the partial derivatives, are with respect to the psi variables, which means with respect to shape. Okay, so what we are probing is precisely the shape dependence of the hydrodynamic interactions. If there's no shape dependence, the curl would be 0, we go nowhere. Okay? Very well. So this is a very, very powerful, I mean, this is in the simplest possible way. I mean, all this analysis is really has, in the general setting, has a lot to benefit from tools in geometric control theory. So this is really control. I'm giving a very simplified. So it's a problem very similar to the problem of the falling cat managing to turn under 0 external torques by rearranging the tensor of inertia. That's exactly what we're doing. We're trying to have translational motion of a system without translational force. Right? So it's exactly something in the same spirit. And one thing that this analysis immediately shows is the non-triviality of the problem, in the sense that, for example, how much will you move? So imagine that psi can vary only a little bit. So we do perturbative things around one shape, and we move psi1 and psi2 only a little. Okay? So we linearize everything. Maybe the curl of V, we consider it's a constant around that state. Okay? And so that integral becomes the area. So curl of V a constant, we integrate over the area, and it's just the area. Right? And so we move with amplitude epsilon. Sorry, we change shape with amplitude epsilon. We move by an amount which is the area. The area of the loop spanned by excursions of amplitude epsilon, which means that we move by epsilon squared. Okay? which tells us that if epsilon is small, epsilon squared will be very small, which tells us that if epsilon changes sign, epsilon squared does not change sign. So if you want to, for example, devise a gearbox, and change direction, we cannot simply invert the sign of epsilon. We have to do something different. And the way of changing direction is to loop in the opposite way. Okay? So not changing the sign of epsilon, but loop in shape space in the opposite way, etc., etc. Okay? So this is very, very rich, and okay, enough for this. Maybe let me just close. Imagine that, as we did, you want to solve the problem of having the three-sphere swimmer, which is a model problem, a model system, and you put yourself in the shoes of an Olympic trainer that wants to win every Olympic race for the three-sphere swimmer for the future. So you want to optimize, right? Not only you want to see whether you move, but you want to move optimally, right? For example, a given energy expense, you want to cover the maximum distance, okay? So that's Olympic racing. So instead of being a control problem, it becomes an optimal control problem, big literature, etc., etc. Now imagine that you want to solve the problem. What you have to do? What you have to do is you have to know this V, for example, right? So everything, all the hydrodynamics is encoded in this vector field. And what these vector fields do is to probe the sensitivity with respect to shape changes of the drag forces. Okay? So what you're doing, in some sense, is you're probing the sensitivity with respect to changes of the geometry of the Dirichlet to normal map. Right? So you are probing the sensitivity of this problem. You want to solve an Navier-Stokes problem. You give the boundary data. You compute the stresses. What you have to do is to know the sensitivity of this map with respect to shape changes. Okay? So something that conceptually amounts to know the solution of Stokes problem, of the outer Stokes problem, for any geometry. Right? So it's an infinite dimensional thing. Right? So you have to know the analog of Stokes formula for this system for any shape. Okay? So it's computationally very intensive. So we have done it brute force, so to speak, but there's a lot to be improved. Okay, so I want to move to crawling. And why did I did this long introduction? Because I want to look at a special system. So let me summarize what we have learned out of this. So what we have learned is that there are cases in which your first bet would be, since the constitutive equation of the medium is linear, Stokes, and so stresses depend linearly on velocities, you would bet that the system is linear, so to speak. And this would, this would cause the fact that periodic shape changes do not produce non-periodic positional changes. And so you need nonlinearity to break this. And what this example has taught us is that even though the constitutive equations are linear, because of the shape dependence, you can get nonlinearity. Okay? Okay. So armed with this piece of knowledge, I want to move to crawling. Okay? So we've done swimming. We've talked about the scallop theorem. And I would like to talk a little bit about this beautiful. Again, this is another, this is not a cell. This is not a cell. So that's a snail. But in similarity with the cell that is crawling on a substrate, it's extracting the horizontal momentum from tangential interaction with a substrate. Like this guy here as well, when I put it very well. Now, snails have been studied very much. And it is known that snails use mucus to propel themselves. So they secrete mucus, so they glide on a layer of mucus. Now, if you think about it, it's sort of, if I think about it, it's quite mind-boggling in the sense that it's like downhill skiing with artificial snow, and they have their own snow-making apparatus on their shoulders, and they snow, and they ski on them, right? It's so what I'm trying to say is that it must be very expensive, right, for the snail to produce this this mucus on which to glide, right? It's like it's like building the road on which you have to go, right? So you and okay, so it's in some sense it's an interesting thought, etc., etc. And it's known that this mucus has special properties. So in particular, it's sticky, and it's not a Newtonian fluid. Okay? So it's a non-Newtonian fluid. And so if you then start thinking about this maybe too naively, you say, oh yes, now I understand why the snail does all this. I mean, has all this. Overcomes all these obstacles and produce its own mucus, because otherwise, I mean, if it had to rely on, say, moisture or water or something, it wouldn't go, right? So maybe non-Newtonian, non-linear constitutive relationships are necessary, maybe. And so maybe there's a snail theorem. Maybe a snail could not glide. Maybe an organism that can only rely on contractions cannot move, cannot have net motion, if the fluid on which it moves is linear constitutive relation, that is Newtonian. Okay? So maybe this is an interesting question, and so we thought of asking this question. And so let's do crawling of model organisms that are one-dimensional objects that can change locally their length. They can contract, like the snail. They have muscles, and locally a fiber, a portion of the one-dimensional thing can contract. So this can be described with this little map here, but I don't want to go too much into the details. So this is the arc length in the deformed configuration. And so it's the position of the first thing plus the distance. And this distance s of x and t can be modulated. So if s of x equals x, then you're doing nothing. You're just reproducing the original shape. If s of x is s prime bigger than 1, you're extending locally. S prime smaller than 1, you're contracting locally. And you can do whatever you want. You can modulate, and I assume that you can do that. Okay? And then I describe the interaction with the substrate with two possibilities. So it's always a force per unit length, little f. It's also always a resistive force. It's always opposite to the velocity. But I consider two possibilities. One is that it's Newtonian-like, so it's linear, so it's just minus mu times the velocity. And another one is represented by this graph in which the force can be nonlinear, and in particular, there's an interval of forces that can be exerted at zero speed, at zero velocity. Okay? So that is the yield value of the force, so that the force you have to exceed in order to move. Okay? Like in friction, like in Bingham fluids. Okay? And so this is what the snail does, actually. The red thing will be the snail. But I want to see whether you can move also in the other case. And so we solve the equation of motion of this thing. And this is the result for the Newtonian case, and this is for the Bingham type case. And we use as condition the fact that we propagate a contractile, I think. This is a contractile wave. We propagate a contractile wave on a little portion of amplitude delta, say, and we move this contracted portion along the body of the swim. Right? And this is the result. Maybe let's look at the graphs. So the graphs over there trace the position of x1 in one case and in the other case. Okay, so let's look at it here. So epsilon 0 equals -1 means a contractile wave of very large amplitude. -1 means that something that is long 1 becomes totally contracted and collapses to 0, right? So it's extremely large deformation. And then we have more moderate deformation like -0.75, -0.5, etc., etc. Okay, so what is this graph telling us? This graph is telling us that in the Newtonian case, the thing moves. Okay? So there is no scallop here. It moves, as always happens in this swimming type things, in an oscillatory way. So the first end, the x1, moves forward and backward, forward and backward, forward and backward, according to this thing. However, if the amplitude of the contraction is large, it can move a lot. And if it's -1, it can move as much as the Bingham case. And the Bingham case is, in some sense, more interesting or actually easy. How does the thing move in the Bingham case? So it does this. It moves only in the contracted part. And now I'm simulating the effect of contracting by going out of plane. But if you think of the projection moves exactly as if it was contracted, as a one-dimensional object that is contracting. And then it propagates this. It propagates the wave, right? So I got a kink and so on. Okay, so this is a mechanism that is linear in the contraction. You move exactly by epsilon 0 delta at each. So you move exactly by the amount you have contracted, epsilon 0 times the length of the region where you're contracted. So this is a linear mechanism in epsilon 0. The other one is a nonlinear mechanism in the contraction amplitude. It's precisely the story about epsilon square and epsilon. And so the two systems are completely different in terms of, in some sense, the behavior with respect to if you want to achieve a change of direction. In fact, you see here. So this graph is meant to suggest the fact that with the Newtonian mechanism, what matters for the sign is the direction of propagation of the wave. So here you see that you change sign to contraction extension. So once you send a contractile wave, another time you send an extensile wave, but traveling the same direction, you get motion in the same direction. While the Bingham case, and you can do the experiment on yourself, is affected by whether you are contractile or extensile. So if I did the same experiment by stretching the paper at the beginning, I would have moved in the opposite direction, right? And this is what the snail does. So it's known that what you see there in the red and blue, so if you take just one red and blue cell, what you're seeing is the pattern of velocities under the belly of a snail, where you see that there are motile parts, parts that are moving in red, and parts that are steady in blue. So which means that the mode is this one and not that one. But all this analysis stems precisely from the same analysis that we did for the swimmers. And let me show you 1 second why. Let's do a simple case in which I don't send a contraction wave, but I do something simpler. Sending a contraction wave is difficult. So I do a piecewise affine case in which I do exactly the analog of the three-sphere swimmer in the crawling case. So I have a snail which is made of two pieces that can be extended or contracted in an affine way. Okay? Something like this. And let's look at the equation of motion. Its total force equals 0. So it's integral along the body of the snail of the force per unit length, little f. Now let's compute this force. Let me compute only in one case the analog of the phi3 that I was doing before. So let's compute the force the snail feels at frozen distances, at frozen lengths. Okay? So what is it? It's the force for the thing moving at unit speed rigidly. Okay? And in the Newtonian case, it's just mu times the velocity. The velocity is a constant, and so it's mu times the length. Okay? So the drag we feel depends on the length. If we drag a fishing net which is 1 meter, we feel a certain drag. If we drag a fishing net which is 1 kilometer, we feel much more drag. Okay? And this is that formula here. The drag depends on the length, but the current length, not the reference length, the current length. And here we have the nonlinear structure. Even though the constitutive equation is linear, and it depends linearly on x star dot, there is shape dependence through the extension of the thing, and we get the nonlinearity. And the structure is exactly the same. So we get the equation, the ODE, that gives us positional change as a function of rate of shape change. We get the V1, V2. We get exactly the loops. We get the displacement out of the curl of that vector field. And here, the curl can even be computed explicitly by hand because the system is very simple. We don't have to solve the equation of motion, the equation, Stokes equation outside. Okay? So, yes. So this is, I look at the watch. So this is mostly of the theory part I wanted to tell you. And I want to give you just two glimpses of, the gap between the story I made, which is, the theoretical tool one can try and use to study these things, and the real thing. Now, the real thing, as I was trying to hint when I was trying to answer to you, is that here I was given shape, I was assigning shape as known. Okay, so I'm God, I say you extend your arms this much. But in the real case, there's a muscle. And so the problem is how much, what is the electrical impulse I give to my muscles in order to produce this shape change, and that's very complicated. So what I'm trying to say is that whenever we look at the real systems, the issue of the motors become very important, as you will be happy to hear. So let me show you a couple of examples in which, instead of looking at big principles, we've tried to look at the issue of how is the shape change actually accomplished in specific biological systems. I will show you one. So this is one of our favorite examples. The reason is because this is it's a protist, so something in between an alga and it's a unicellular organism that has flagella, but it's also some form and can swim in quotes by moving the flagella. But it's also another form of motility, which is called metaboly or euglenoid movement, in which it moves by changing shape a lot. It's not a sausage with the flagellum, but the sausage changes a lot and the flagellum does little. And this is something that is not very well understood. It's not clear what is the biological function, at least to the best of my knowledge, etc. So the first step is conceptually exactly the one I've been talking up to now. You have shape change. Maybe you measure shape change. You put it in a code. You solve for the Stokes equation outside, and you get the stresses, and you get the way the thing moves. Okay? In principle. The thing has gone, sorry. Okay? So you saw the way the thing was moving, and essentially it moves by propagating a bulge on the body. Okay? Which makes you think that the way it moves is similar to when we do this. Okay? Imagine that my arms have not a rigid, a fixed point here, but I can move my arms, down. I would propagate a bulge through my body, and I would propel myself. Right? However, if you look at, okay, now you want to understand whether this has anything to do with reality, and it has no. So there's no way this organism this organism doesn't have the muscles or the internal architecture to produce. There's no. The mechanism I was indicating is completely unrealistic. There's no appendage that moves along the body. And so if you start looking at micrographs, you start seeing that you cannot see from there, because for some reason these pellicles that you see here do not show there, typically. You can just see traces, but not quite. They are transparent in some sense. But if you look at them, it's CEN, you see them. And so, okay, our idea was to see whether the engine was here, whether the motors were the strips, whether the way the thing was accomplishing the shape change were the strips. Because this analogy has nothing to do. There's nothing like an arm in the things. And so we had to devise this. And we noticed the fact that there seems to be a correlation between the orientation of the strips and the diameter. So this is an essentially axisymmetric object, and its radius or its diameter seems to be correlated with the inclination of the strips. I don't know whether, it's very faint, but maybe here you can see that the strips are almost vertical, and here, highlighted by this red line, they are almost horizontal. Okay? So there seems to be a correlation between the orientation of the strips and the things, and so we thought, okay, Of course, I'm simplifying the story. This is, somebody else had suggested this as well. So the possibility is that the strips slide one against each other, and because of the sliding of the strips, the shear stresses, the shear strains actually, that would be produced by this sliding, generate this bulge. Okay? So we tested this assumption by imagining a localized pattern of shear between the pellicles. We described it as a continuous thing. We sent a traveling wave of shear in a similar way as before I was describing a traveling wave of contraction. And we simulated the motion of this object under this. And we could reproduce many observations. So this is the way the thing would move according to us. And the engine for this system would be the following. So this is taken from the literature. So these are the strips I was mentioning. The plasma membrane bridges between successive strips, but it's a fluid membrane, so it doesn't, it's not, and under these strips, there should be microtubules, and microtubules have motors. They're motors that can have microtubule slide, and this would be a possible motor for this system. So as you can see, it's very far away from the first idea you get out of seeing the movie of the object. So just to close, I want to talk a little bit about this as well, which is the real goal. So the crawling cell, etc., and for which the motor is actin polymerization. Right? So we know that these things move. Okay, we sort of know that these things move thanks to the fact that at the leading edge there's polymerization, and this is the thing that pushes the leading edge. Okay, so we have made a study of this with the idea that it could be. So what is the big question here? Maybe in 2 minutes I can say it. So what is the question here? So the idea is the following. Metaphor for this is walking inside a balloon. Okay, and we move the balloon, so the treadmilling, etc. We move the balloon by pushing. Okay, and this pushing is done by polymerization reaction at the tip of the actin filament. So monomers are added, and this is the thing that produces the propulsive force. So many questions, many questions, many talks in this workshop have been addressed to this. So the basic question is, how is it possible that out of polymerization reactions that take place in one filament, one actin filament is of the order of 7 nanometers thick. So how is it that uncoordinated individual polymerization reaction result into the advancement of a front which is 50 microns? There's many filaments. So how is this, okay, there's many, so who's the orchestra director, right? So there's many possible answers to this. The thing we want to explore is whether mechanical interactions, so the fact that all these filaments are pushing against the same membrane, so the mechanical stresses through the membrane could be the organizing principle. And what we found is that if you insert in the system the fact that filaments may break if they grow alone, then you can get coordination. So in some sense, synchronous growth can emerge out of the evolutionary principle that if you grow in isolation, you push against something and you break. And until you push together and through mechanical interaction, you sustain each other's action, then this is a way in which coordination may emerge. Maybe I can talk about this in private with people that are interested, and I thank you for your attention.
Yeah, they're really fascinating. So one of the last films you showed was these linear motors on the euglenoid, and they look like locks of drums. They sort of spiral. You depicted them as having a single-handedness. Do they, in your model, are they actually pairs that are crossed? That's the first question. You know what I'm referring to, yeah. And so the second question is sort of although these linear motors were spiraling, handedness, whatever, helical, the shape itself was a surface of revolution. And back to your Olympic swimmer champion, I mean, is there reason to expect that the optimal shape is actually a surface of revolution, or might it also have, as you see in some of the actual biological systems, some kind of a helical structure, the shape? Is there any sense of what the optimal shape of the euglenoid is?
Yeah, I'll try to answer quickly.
Yeah.
So we're at the early stages of this.
Sure.
So the only thing we've done is somehow to check the feasibility of sliding as a mechanism to produce traveling bulges. Now, whether there are crossings, I don't think. I've never seen crossings of motors, but I don't think that we need to think and look a lot. So I would not say much more. We need to learn. So we don't know what's really happening. Regarding the axisymmetry, again, was just the first attempt. We know that, and you've seen also pictures in which axisymmetry is not preserved. In fact, this is an interesting thing, because by leaving axisymmetry, you can generate lots of more interesting shapes, like bananas and so we are exploring now this as a concept, right? To morph objects by a different mechanism, which is localized shear, and shears within the surface.
So I believe that you have to give another talk. Because you will not give all answers on all these questions. This especially, this was a fascinating thing at the end, which we would like to hear it again. So thank you.
Thank you.